So I want to take some time and talk about some properties of the complex log. And in particular, what I want to do is I want to recall that if you have the complex exponential, you have to define what's called a branch. In our case, we're going to use what's called the principal branch, which is from negative pi to pi. But really, any interval of length 2 pi will do. You can also define the complex logarithm. That's defined as the natural log of the modulus of z plus I times the argument of z. And so I want to show you a few properties of complex logarithms here. The first is, let's say that z is x plus iy. In that case, then e to the z is going to be e to the x plus iy, which we know is going to be e to the x times e to the iy. In other words, the modulus of e to the z is going to be e to the x. This is a real valued term. And then the argument of e to the z is going to be y. Okay, and so that's the angle that that's going to make. Okay, and so in particular, if we take log of e to the z, just by definition, this is going to be the natural log of the modulus of e to the z plus I times the argument of e to the z. And so that's going to be the natural log of e to the x plus I times, well, the argument of e to the z we said is y. And the natural log of e to the x, this is now just the real valued natural log function. E to the x is a positive real number, so this is just going to be x plus iy. So we get back the value z. And so that tells us that log of e to the z is going to be z. There was a little bit of subtlety here, which I glossed over, but that was specifically when we talked about the argument, that was just y, and y has got to be in the certain range that we have. Okay, so the argument for the exponential function has to have those values between negative pi and pi. Likewise, we can look at e. So now let's look at e to the log of z. And what we're going to do here is let's write z is r e to the I theta. And we'll do that. We'll do e to the log of r e to the I theta. The log of a complex number is the natural log of the modulus, which in our case is going to be r, plus I times the argument, which is going to be theta. Okay, and so that's going to be e to the natural log of r times e to the I theta, and that's r e to the I theta, or z. So it turns out that e to the log of z is z, and log of e to the z is z. Okay, so these are both important. And they tell us that the complex logarithm and the complex exponential are inverses if we restrict if we make a determination of a branch cut, okay, for the inputs for the exponential. So this is the first two things that I wanted to show you, is that these logs are, logs in complex exponentials are inverses. The next thing I want to do is I want to prove that if, say, w and z are complex numbers not equal to 0, then let's look at the log of w times z. And I want to look at what's that log going to be. And so the log of w times z, what we can do is we can look at, this is going to be the natural log of the argument of w times, the natural log of the modulus, I mean, plus I times the argument of wz. And we know a few things about the modulus and a few things about the argument. And so this is going to turn out to be, let's see, this is going to turn out to be the natural log of the argument of w plus the natural log of the argument of z plus I times the argument of z plus the argument of w. You know that when you multiply two complex numbers, you add the angles, right? You add the arguments, and that's basically what we just said there. And then we can regroup just slightly. This is going to be the natural log of w plus I arg w plus the natural log of the modulus of z plus I arg z. And this is slightly tricky here, but what I've written so far is completely fine. Now, the one little thing that we have to be careful of is that this is the log of w plus the log of z plus possibly something else, but that something else has to be possibly some number of the form 2 pi I k. So in other words, it's possible if we have two numbers that when you multiply the, so let's say that we're looking at just the branch from negative pi over pi to pi. Okay, so we know that when we multiply the two numbers, let's say we have, just to make this concrete, let's say that we have two numbers that are, say, 3 pi over 4. Okay, so those are the two values. Well, if I were to multiply those two values that both have the argument 3 pi over 4, those are both values that are in our branch that we're talking about, because our branch goes from negative pi to pi. 3/4 of pi is less than pi. But if we were to multiply them, then we get a value that's outside that branch. We get a value that would be 3/2 pi, okay, which is a little bit bigger. And so you would have an extra term here corresponding to the fact that we kind of left that, we left the range of values for the argument that we're allowed to use. So the point here is that, let me just write this nicely. So in conclusion, what we just showed is that if w and z are non-zero complex numbers, then we have the usual rules for logarithms, that log of w times z is the log of w plus the log of z, plus possibly a multiple of an integer multiple of 2 pi I. Okay, so plus possibly a integer multiple of 2 pi. Okay, and so this is complex logarithm. So that rule also works